In the previous video, we learned how polarity relates to molecular structure. Today, we're going to close out Unit 2 by looking at hydrogen bonding. So far, we've looked into three types of chemical bonding. We have ionic bonding, covalent bonding, and metallic bonding. Of these, ionic and covalent bonding are the most important. The main characteristic that ionic and covalent bonding have in common is that both involve valence electrons. Atoms want to achieve a full valence electron shell, so they share electrons. The bonding we're looking at today works a bit differently. Instead of forming bonds between atoms based on the sharing of their valence electrons, hydrogen bonding is a type of intermolecular bonding that is based on electrostatic attractions between molecules that have opposite partial charges. There are two main parts to this definition. The first half is that hydrogen bonds form between molecules. It is a type of intermolecular bonding. The second half is that electrostatic attractions are the driving force behind hydrogen bonds. Electrostatic forces, remember, are the attractive forces that form between particles with a positive charge and particles with a negative charge. In terms of hydrogen bonding specifically, hydrogen bonds form when there are two molecules in close proximity to one another. One of these molecules involves a hydrogen atom that is bonded to a highly electronegative atom, such as nitrogen, oxygen, and so on. Essentially what happens is, the large difference in electronegativities between hydrogen and the other atom gives a partial positive charge to the hydrogen atom and a partial negative charge to the highly electronegative atom. Let's think a bit more about this. Why does this happen? There are two parts to any hydrogen bond. First, we need a hydrogen atom that is covalently bonded to an atom with a high electronegativity. This makes them a molecule. Then, we need a second molecule. This molecule contains at least one atom with a high electronegativity that also happens to carry a lone pair, or a pair of non-bonding electrons. This creates two regions of partial charge. The positive region surrounds the hydrogen atom because it is involved in a very polar covalent bond. The negative region surrounds the atom with the lone pair, since those two electrons add a small negative charge. An attraction then forms between the hydrogen atom and the atom with the lone pairs. Here's an example to illustrate this. This is quite a common example actually, probably the most common example of hydrogen bonding there is in nature. What we're looking at are three water molecules. Water is a polar compound because oxygen is significantly more electronegative than hydrogen. There are also two lone pairs on the oxygen atom. This creates a total of 4 regions, each possessing a partial charge. Let's focus on this one water molecule over here on the left. This molecule will have 4 regions of partial charge, 2 positive and 2 negative. The 2 positively charged regions are around these 2 hydrogen atoms, 1 partial positive charge on each. The 2 negatively charged regions surround these 2 lone pairs, 1 partial negative charge on each. This means that a total of 4 hydrogen bonds can form between this one water molecule and its fellow water molecules over here. This is actually what happens inside any quantity of water. Whenever water molecules get close together, they establish these hydrogen bonds, and these bonds help them stick together. It's important to mention that because hydrogen bonding relies on electrostatic attractions as opposed to the sharing of electrons, it is weaker on average than either ionic or covalent bonding. We'll talk more about the average relative strengths of different types of bonds at the end of this video. It's also important to remember that hydrogen bonding doesn't create new compounds. When these water molecules form these hydrogen bonds, for instance, they don't become some kind of triple water molecule or something like that. They're just water molecules that are interacting with one another. That's honestly the best way to think about hydrogen bonding. It's an interaction. hydrogen bonding is classified as a type of intermolecular bonding because it occurs between molecules. It is not, however, the only type of interaction that can happen between molecules. The collective term for all intermolecular bonding or interactions is to call them van der Waals forces, named for the Dutch physicist Johannes van der Waals. In addition to hydrogen bonding, there's a second type of intermolecular interaction called a dipole-dipole interaction. These interactions happen when two polar molecules get close together. The polarity of the bond creates regions of positive and negative partial charges on the two molecules, and a temporary interaction forms between the ends with opposing charges. In this drawing, the electronegativity of the atoms drawn in red is much higher than the En of the blue atoms, so a polar bond forms. These two molecules then begin to draw closer together because of the electrostatic attraction between them. The last type of intermolecular or van der Waals forces are called London dispersion forces. These forces occur due to an unequal distribution of electrons inside bonded atoms. We know that electrons follow orbitals inside atoms, but sometimes all the electrons will be at a point in their spin where they are all on the same side. This creates a tiny partial charge. The area with a higher density of electrons gets a negative partial charge, and the area with an absence of electrons gets a positive partial charge. These partial charges are really small, but they are enough to facilitate an intermolecular interaction, as shown here. Some viewers might be curious as to why they're called London dispersion forces. The name actually doesn't come from the city of London. It's actually named for Fritz London, a German physicist who served as a professor at Duke University. There are three universal statements that we can apply to all van der Waals forces or intermolecular interactions. The first is that all are attractive in nature. We know this because all intermolecular interactions are based on electrostatic forces, and opposites attract. Now, there are some rare circumstances in which van der Waals forces can be repulsive and push molecules away from one another. This usually happens at extremely high pressures and other conditions that we aren't likely to encounter in everyday life. For the purposes of the average general chemistry course, it's enough to remember that in general, van der Waals forces are attractive. The second statement is that all van der Waals forces are weaker than both ionic and covalent bonding. Sharing electrons is going to create a stronger bond between atoms than being electrostatically attracted. Our third and final statement is that the strength of all van der Waals forces is inversely proportional to the distance between the molecules being considered. We might remember from our math classes that if two variables are inversely proportional, one decreases when the other increases, and vice versa. For example, we might say that there is an inversely proportional relationship between the amount of money a person spends and the amount of money said person is able to save. The more you spend, the less money is available for you to put into a savings account, retirement account, investment account, whatever it is. In this case, the further two molecules are from one another, the weaker the intermolecular interactions between them. Distance does not make the heart grow fonder as far as molecules are concerned. This is a brief recap of everything we've looked at so far. We examined two types of forces or interactions: intramolecular forces and intermolecular forces. Intramolecular forces happen inside a molecule, between the atoms that comprise it. The three types of intramolecular forces are ionic, covalent, and metallic bonding. Intermolecular forces, by contrast, happen between molecules. They are often referred to as van der Waals forces. The three primary types are hydrogen bonding, dipole-dipole interactions, and London dispersion forces. Down here, we have a table which contains all the interactions and forces we've described thus far. These are average strengths, but they should be accurate in most cases and under most physical conditions. Going from strongest to weakest, we have ionic bonds, polar covalent bonds, non-polar covalent bonds, metallic bonds, hydrogen bonds, dipole-dipole interactions, and London dispersion forces. In the next video, we begin Unit 3 with Video 1, covering the mole. Thank you for watching.